Afternoon, everybody. My name is Joe Manning from the Departments of History and Classics. What's an historian like me doing in a place like this? I think we're going to find out over the next hour why I'm so attracted to this sort of work. And thanks for coming out today. This is year 2 of what I call the Yale Nile Initiative, which is an excuse to talk about history and paleoclimate altogether, around not just the Nile River Basin, but more broadly as well. And I am really thrilled to be able to welcome Joe McConnell from the Desert Research Institute here today to kind of kick us off this year. Joe is a research professor in the hydrology division of the Desert Research Institute, very well known to everyone in ice core science kind of broadly, a real pioneer in continuous flow analysis. His lab is really famous for having 2 ICP-MSs, which when I see these things as an historian, they're kind of magic boxes. These are amazing machines, and I think the only lab in the world that allows real data to be visualized, or data to be visualized in real time, which is spectacular. I'm taking some of my students out there in about 3 weeks, and we're really excited to go out there and have fun with ice core analysis. Joe, besides just basic ice core science, of course, the last few years he's gotten hooked on doing history and archaeology, and we're really grateful in the ancient history community for all kinds of reasons. It's Michael Siegel, a postdoc in Joe's lab, and Joe is an author as well, in Nature from 3 years ago on a new chronology of the volcanic eruptions in Antarctic and Greenland ice that revolutionized pre-industrial history, I think. It's one of the most important papers in ancient history in decades, I think. I make all my students read it because it's fundamentally important. And when did this come out, Joe? A few months ago, in the Proceedings of the National Academy of Sciences, this fundamentally interesting paper, Lead Pollution Recorded in Greenland Ice Indicates European Emissions Tracked Plagues, Wars, and Imperial Expansion During Antiquity. This is a phenomenally interesting paper. It's lit up the world of Iron Age archaeology, and in particular Roman historians. And it really is sort of a first sort of paper that's going to generate, I think, years of research in Roman history and the first millennium BC worlds, let alone work in ice core analysis. So with that as a brief introduction, I will turn the floor over to Dr. Joe McConnell.
Okay, can you hear me okay? Yeah? Thank you all for coming, and thanks to Joe Manning for the invitation. I was telling Brian Skinner a minute ago that I first set foot on Yale campus and in this lecture hall 40 years ago this month. Hard to believe, and it was to hear Brian give his introductory geology class. So anyway. Who would have thought I'd be here talking about history? But anyway. Okay, so I'm going to talk about the title is Ancient History and Ice. I have 2 primary collaborators on the work that I'm going to talk about. Andrew Wilson, some of you historians may know him at Oxford, and Andreas Stoll is a very well-known atmospheric modeler in Norway at the Norwegian Institute of Air Research. And then we had other co-authors, a couple people, Monica and Nathan from my group, Sabina Eckhart from NILU as well, a couple more people from Oxford, Elizabeth and Mark Pollard, and then J.P. Stephenson from the University of Copenhagen. Definitely very much a collaborative effort. Funding, always have to acknowledge the funding. So most of the work that I do is funded by NSF, some by NASA, but most of it by NSF, Arctic and Antarctic programs. I've made about 25 trips to Greenland over the last 25 years and about more than 10 trips to Antarctic funded by these programs. So the specific work, most of the specific work I'm going to be talking about today was funded by the John Feld Fund at Oxford and the Desert Research Institute, my institute. So some of you may know, some of the historians may know that in the 90s, people measured lead in ice, in Greenland ice, Rossmann et al. In 97 and Hong et al. In 94. And they published this record. This was the Rossmann record. So this is concentration. These are isotopes on this axis. And you can see that during 1000 BC to 1600 AD, it looks like, and you can see there was this increase during the Greek and Roman period and a drop in the isotopes. And this created a lot of buzz in the ancient historian world about what information you could get from ice. And as a result of that, well, this is just another graph of the same data, those same concentration points. And so these guys measured 18 measurements over this 18 or 1900 year period. And each measurement represented what they thought was 2 years of ice. So that was the record that historians were using for these studies of the Roman economy and the Greek economy and so forth. And after that, so Andrew Wilson and Mark Pollard from Oxford came to me because they knew I could measure lead very accurately in ice. And this is the record that we developed. And this is what I'm going to be talking sort of around and about today. And you can see you get a very different picture of lead pollution in Greenland from this much, much higher resolution record. And so our measurements have, instead of having 18, we have 21,000 measurements across the same time period, and we have about 12 measurements per year during antiquity, okay? So it's a very different record that gives you a much different picture, but you can see that the concentrations are pretty much in agreement. It's very much in agreement with the previous work. So an outline of what I'm going to talk about, because this is kind of a mixed audience of earth scientists and historians, I thought I'd kind of try to thread the needle between the two. I'm going to talk about the archive of past environmental change in glacier ice, just to kind of bring you up to speed with that. And then I'm going to talk about continuous lead record during antiquity, the specific paper that Joe referred to, and then some conclusions and future plans. So imagine you're standing on an ice sheet. There's snow falling around you. It's going to pile up around your feet, and it's going to be very low density, fluffy stuff. As time goes by, it's going to start to age and be buried, and that's going to form a surface layer that's harder and more compact. Eventually, this thing is going to squeeze down, trapping air bubbles and then the ice. And eventually, at about 60 to 110 meters, depending on the site, you're going to turn from firn or old snow into ice. So you're going to close the pores off, the air bubbles off. And then you're going to trap at that point some picture of the atmosphere at that time, right? And these are the seminal records that you hear about in climate change science of carbon dioxide and carbon monoxide and methane. So really fundamental cornerstones of climate change science. Well, different than that is what's in the precipitation itself. So that's the water isotopes. And water isotopes we use as a proxy of temperature, of site temperature. Very well known, again, very much a cornerstone of climate change science, comparing especially water isotopes to the gas records, right? In addition to that, you get sea spray, you get aerosols, so-called aerosols. And by aerosols, I mean very small droplets or particles that are in the air all around us. They come from, in the natural world, things like sea spray and dust. And then in the more recent period, maybe the last 3,000 years, you get pollutants. And so I was just going to show you this quick little part of the simulation. This is a simulation from NASA, and it's a simulation of aerosols moving around the Earth. Some of you may have seen it. In this, you can see down here, sea salts are coated blue, desert dust is red, organic and black carbon is green, and then the sulfates in white. And just as you're watching it, you can see things coming off of biomass burning plumes in Africa and South America. You can see dust coming off the Sahel and the Sahara. And you can see pollutants and so forth. And I won't run it for very long, I don't think. Let's see if this is going to work. So I personally find this very mesmerizing. It's kind of like watching a fire. You can see everything kind of swirling around. So you can see, as an example, you can see the big sea salt storms encircling Antarctica, right, sweeping around there. You can see sulfates coming off of the industrial parts of North America, Western Europe, and Asia. You can see here's the dust, the big dust swirls coming off of the Sahel and sweeping out over the Atlantic and fertilizing it. And then watch here, you can see these big biomass burning plumes coming off of these regions. Now, some of that aerosol, not much of it, but quite a small percentage of it actually, ends up getting swept up over the Greenland and Antarctic continents and gets deposited with the precipitation or gets dry deposited onto the snow and gets buried, and that's what we measure with the ice core, right? So, and then every once in a while, just to make sure everybody's on the same page, every once in a while you get a nuclear explosion, which we know very well about in Nevada. You get a nuclear explosion, or you get a cosmic ray burst in the upper atmosphere, or you get a volcanic eruption that creates a sulfur, increase in sulfur in the atmosphere. And those get deposited all around the Earth pretty much at the same time, and that gives you an isochrone that we can then use for cross-dating ice cores. We can use it for confirming our dating, and we can use it for synchronizing to other archives, things like lake sediments or ocean sediments and things like that. So then we go and drill an ice core, and you can see we're just going to drill an ice core from the top to the bottom. The ice at the top is the age of when we drilled the ice core here. So whatever date we started drilling, and it's just going to go down however far. I think the longest ice core is about 3.4 kilometers long. So this is just going to penetrate ice down 3.4 kilometers for a couple of miles. This is just a quick schematic of what a glacier or an ice sheet looks like, in this case an ice sheet. So you can divide it into sort of two zones, the accumulation zone. So that's where you're in positive surface mass balance, so more snow is falling out of the sky than is melting. And so that's where you're building up layers year after year after year. You have the ablation zone where the opposite is the case. You have negative mass balance. In order to keep this thing at steady state, you have to transport through flow, ice flow, you have to transport mass from the accumulation zone into the ablation zone. So you can imagine normally we would go to the accumulation zones to drill ice cores because we want layers piling up year after year. We don't want to be missing years, or we don't want to have negative mass balance. I should add that these days there is quite a bit of work going on in the ablation zones, and that's because you don't have to drill through hundreds or thousands of meters of snow to get to the old stuff. The old stuff is exposed right at the surface. So if you want big samples, typically nowadays you go to the ablation zones. You can imagine it's very difficult to date this ice. So there's a lot of flow distortion, and then there's also the dating issue. But there is quite a bit of work going on in that area. So I just thought I'd say a little bit about sampling the archive. So that you can imagine I divided up into three different methods or sort of scales. The deep sampling is, this is a millennial scale or multi-millennial scale work. This is an example at Sipel Dome. So these are big projects, might take 4 to 5, 6 years. They usually involve multiple institutions and often involve multiple countries. So big operations cost tens of millions of dollars. This is another example from the Danish group. The Danes do a lot of drilling in Greenland because of their historical connection to Greenland. This is the camp in 2011 at Nîmes. And so this is the geodesic dome they had built, and it's pretty neat. You live in this thing. This is the galley. You don't work in this part. You just live here and recreate there and so forth. And they've now put this thing on skis, and so they can drag it around the ice sheet. So this has been dragged to the other side of the ice sheet and is now being used in the EGRIPT project. Anyway, so a really neat building, and I'm amazed that they're able to drag it across the ice sheet. But you can see a C-130, a US LC-130 there, a ski plane, and that's for the heavy lift capacity to provide the logistics for the camp. Now, most of the work, as I said, we just recreate in this building. Most of the work actually happens in trenches, and these are, maybe 30 feet or 10 meters deep that are used a snowblower to make them. And then you cover them over, and you can see the advantages or the disadvantages that it's cold and you feel like a troglodyte in there. The advantage, though, is the weather can be doing anything upstairs, and you have no idea what it is, so you can work in any environments. This is the deep drill, so this drill will eventually go down 2.8 kilometers. So. And then the intermediate sampling would be maybe 100 to 200 meter long cores. And by the way, the total depth is 200 meters. We handle it in typically 1 meter sections. So anyway, my group has done a lot of this kind of work, including the Arctic Circle Traverse, where we went by snowmobile across Greenland, collecting ice cores and doing radar surveys. Might take you, let's say, a few days to a week or two to drill a 100 to 200 meter core. And then I've also done some work. This is with the Australians at Aurora Basin in East Antarctica. And you can see this is the camp. They're the buildings where we work, and these are all the sleeping tents. Everybody has their own sleeping tent to have some privacy, get away from people a little bit. Supplied by, not by C-130, but supplied by Basler aircraft. It's a stretch DC-3. And then this is the drilling operation, so this very small little drilling tent, again, embedded a little bit into the snow. This is the old surface right here. and a tent so you can work in any environment. And you can see this is Christmas dinner. It's not too bad. Life is pretty good. We got wine. We got pretty good shape. And then if you're really good, Santa Claus will show up and you can, you've got to be good. Anyway, and then there's sampling, shallow sampling, and my group this was originally what we sort of specialized in. And these would be maybe 30-meter cores. So maybe you're looking at a decades to maybe 1 century long record. And this is a technique that I developed called commuter coring. And the reason was that when we first started doing this, we would get taken out by a ski plane, a Twin Otter like this on skis. We'd get dropped off with all of our camping gear. Plane would go away, and a couple days later, if we're lucky, they'd come back and get us. But at one point in time, at the beginning of the project, we were on our 4th of 8 sites, and we got stuck for a week at a site, and our generator was giving out, and our stoves were giving out. It was touch and go. Anyway, so I came up with this idea of keeping that $20 million plane and the pilots with us. So they don't get to leave, and they're not going to leave us out there in that situation. So the key is to be home in time for dinner, and then if you're stuck or whatever, by the weather or by broken planes or whatever, you're stuck on the coast. So it's much safer, and it's actually cheaper because you're flying out full of empty ice core boxes and camping gear and so forth. You get dropped off, you do your work. I mean, you don't get dropped off, you do your work, and you fly back light on fuel and heavy on ice cores. So it only takes 1 round trip instead of 2 round trips. So NASA loved us because of this. Now you can imagine you're a pilot or a co-pilot, and you're sitting up there, and it's about minus 25, minus 30, and you think, well, what am I going to do? You can sit in the plane and watch us and get really cold, or you can help us. And so there's the co-pilot, the pilot. It makes a big difference, especially when you get a really big, strong Danish pilot who can lift, or co-pilot who can lift anything. So, ice core analysis, I just thought I'd say a little bit about ice core analysis. So in the old days, as in this record we were talking about earlier from Rossmann, these were their 18 points that they measured over this 1900-year period, right? 18 measurements, 2 years each. Now, why would they measure so little, make so few measurements? Fundamental question, right? Well, the reason was because they were doing discrete sample analysis. And for metals, very, very low levels of metals, they were loading up a piece of ice right here into a lathe. That's a hand lathe. And they were scraping very carefully by hand. They were chiseling off ice and catching it in this little bucket. So they're all dressed up in their clean gear and all that sort of thing, working under a laminar bench and so forth. And they're slowly scraping this off and progressively working their way towards the uncontaminated inner part of the ice. You can imagine, hugely time intensive. I've been told that it took Song-Ming Hong and colleagues up to 6 months to chisel those 18 samples. It's a big deal, right? Well, we have gotten around that now, and that's why we have so many more samples like this by using continuous analysis, and Joe alluded to it a minute ago. So continuous analysis rather than discrete. And in this case, we're going to use, so let's back up a little bit. So here's the cylindrical core. So you can imagine a cylindrical core about 10 centimeters in diameter, 1 meter long. We're going to cut from that approximately 3.3 by 3.3 centimeter by 1 meter long, 100 centimeter long stick of ice. It's like this long stick. And we can cut, in one project, we actually cut 7 of those sticks from one 10-centimeter core. So we can analyze the core over and over again. We don't use anywhere near all the ice on one analysis. Then we're going to clean the ends very carefully, as you can see here. For those of you who know who Michael Siegel is, he's the hand model here. We're going to use, this is a ceramic potato peeler you can buy from Amazon or whatever. But it's really important that we get the ends really clean, and so ceramic is really the only way to go, that we can get it clean enough for these metals. And then we're going to load that stick. So there's that stick I was talking about. We're going to load it up into this melter stand here that we developed. And the ice is just going to fall by gravity down onto this heated melter plate. I'll show you in a second. So here's the melter plate down here. It's just going to fall by gravity. The melter plate is the temperature is controlled very carefully. And that water is going to melt, and we're going to suck it off and analyze it in real time in about $1 million worth of analytical equipment. Let's see. Whoop. What am I doing here? So This is what the melter head looks like. And so you can see that about the 3.3 by 3.3 centimeter stick of ice sits on top of it. These ridges that are engraved into the melter head separate the meltwater into different sections. The innermost 10% is what we analyze using those high-resolution ICP-MSs that Joe mentioned for elemental measurements. The next 20% or so, we're going to pump off into a whole bank of instruments that we measure things like nitrate and sulfate, nitrate and ammonium, and things that are water isotopes, things that are very difficult to contaminate and occur at much higher levels. And then the final 70%, the outer 70%, we're going to throw away as potentially contaminated. So instead of chiseling day after day, month after month, we're going to use the melter system to clean the ice, to decontaminate the ice. So we're only going to use that innermost 10%. Well, the difference is we don't have to chisel. It just happens in real time. It's fantastic. Yeah, so let me show you. Let's see, where are we next? No, so this is a schematic, and I won't bore you with the details here, but this is a schematic. There's the melter stand in the cold room. Falls down onto the melter head. We take that 10% inner part and send it off to this kind of setup. So the two ICP-MSs right here. We collect fractions for later on analysis if we want as an archive. And then the other part we send over this direction. In this particular case, I'm showing that this is our gas method. We don't do the gas measurements ourselves. So we used to think of those gases that were bubbling out of the water, we used to think of that as a waste product and be annoyed by it because we don't want those air bubbles to go through our system. But starting about 4 or 5 years ago now, the Danes and the French and the people at Oregon State were developing methods to measure that gas in continuous mode as well. And it's all a function of technology. It's cavity ring down measurement systems that make it possible. But so now we can get methane and CO measurements continuously as part of this whole thing. So out of that little stick of ice, we can get about 35 different measurements of elements and chemical species, and then as well as the gases and the water isotopes, all out of that little 3.3 by 3.3 stick of ice. So it's really revolutionized our industry in that we can get so much information out of so little ice, and that saves other ice for other applications. For those who are interested, this is sort of what we're doing with the periodic table nowadays. So the ones that are in solid circles, we routinely measure. So we're covering a pretty good part of the periodic table. The ones that are dashed, like plutonium down here, we only measure that under special circumstances. Just as a little aside, the plutonium, we published a paper last year, maybe the year before, on continuous measurements of plutonium. And so what we're doing that for is to try to see the bomb pulses, the 54 to 63 period of thermonuclear testing. And we need that. We'd like to know that for the thermonuclear perspective, but also for dating ice cores. And we came up with a continuous method for that, but the height of the peak of the bomb pulse period is 1 part per quadrillion. So that's 1 gram in 10 to the 15th grams of plutonium. To make that measurement is extremely sensitive analytical equipment. So let me just show you this little video of the lab, just to give you a picture worth 1,000 words kind of thing. The first couple of seconds is green for some unknown reason. It'll change here. So this is Nathan, one of my PhD students, working on the core. And so he's just shaving it down to make sure it'll fit in the melter stand. So that's 1 meter long, about 3.3 by 3.3 in cross section. You can imagine in the ice, we can't tell what's up or down. So until we analyze it. And so we want to keep up. So up is always to the right. And he's put that X in there to mark the top of the core so we can keep track of it as it goes through the melter. And now he's cleaning the ends very carefully because the ends are going to go into the melter system. They're not going to get thrown away as part of that 70%. So since that's going into the analytical system, we need it to be really, really clean, very, very clean. So he's done that. Now we've loaded it up into the melter stand. You can see the ice poking out the top there. It's falling by gravity down onto the melter head and slowly melting. I should add that the melter head is made out of a ceramic, a silica carbide, so you can clean it with conch acid and all that sort of thing, and we do routinely. This is it sped up, obviously, but there's the ice falling through the melter head. There's time right there. And you can see Nathan's whipping in there. He's very fast. And you can just see the ice. And so you can imagine we can generate data incredibly quickly compared to the old days. In fact, my group is sort of swimming in data. We can't, the group is not big enough to publish all these data in a timely way. So if you need data, talk to me. So anyway, so then you can see the water's being pumped and the air bubbles and so forth are being pumped. into different analytical systems. When my students first or postdocs first see this, they freak out because of all that spaghetti. But after you get used to it, it's pretty clear how it works. So you can see all the gas-water mixture is getting pumped through the whole system. And then we go through bubble detectors to determine the air-water mixture we're seeing and that sort of thing. And those of you in Joe's seminar will see all this and get to scrape ice yourselves here soon. And then in this case, we're doing gases, so you can see the bubbles going into that one debubbler, and that's sealed, so the gas is going out the top. So I think that's it. Okay, so I hope I've covered that first part, what the archive is, how it's formed, some of the issues, accumulation versus ablation zone, that kind of thing, how we sample that with different scales, and then our discrete versus continuous analysis. So now I thought I'd talk a little bit about this lead during antiquity story. And it's, there are some extremely important steps in all this, so I'm not just going to go straight to the record. So this is the paper that Joe alluded to or mentioned. And it was, as I said earlier, it was a collaboration with historians at Oxford, archaeologists at Oxford, our group, the Norwegian Institute for Air Research, and the University of Copenhagen, and their main contribution is they provided us with the ice, so a very important contribution. So first of all, so the question we're going to ask is, what does Greenland lead pollution tell us about ancient economies during antiquity? First question, who cares, right? Well, I hope this audience cares. I hope I don't have to convince you. But certainly ancient and economic historians and political scientists and archaeologists would like to know some quantitative information about ancient economies and what controlled them or what drove increases and decreases in economic activity. So, as environmental scientists, of course, we'd also like to know, assess human impacts, and the idea that humans were having a measurable impact on the environment 2,000 or 3,000 years ago is not something that you kind of take lightly. Why lead? Well, lead, it turns out, was that most of the silver that existed in, most of the silver that was mined by the Romans, and they wanted silver for their coinage because they were silver-based coinage. Most of that silver occurred as as galena ores, so lead-silver combination. And pretty much sort of rule of thumb, for every gram of silver they produced 99 grams of lead. And lead with its lower boiling point was easily, a lot of it escaped and was into the atmosphere, was emitted into the atmosphere and transported around the Earth. Another nice thing about lead is it has very low background levels in the natural environment. The other primary sources would be dust, continental dust, so just the lead occurring in dust or rock. And then also some volcanic eruptions have a significant amount of lead in them. The other thing, as I mentioned, we have a little bit, is we have very low detection limits. So when we were doing this experiment, we can reconfigure this depending on what our scientific objectives are on a particular project. And in this case, we took this low-resolution ICP-MS, and we only used it for lead measurements. Actually, thallium, lead, and bismuth was the suite. And by doing that, we were able to get lots and lots of measurements and end up with a detection limit on the order of about 0.01 picograms per gram. So that's 10 to the minus 12 grams per gram. So very, very low levels and very important for this kind of work. As I mentioned, I think we analyzed a total of 423 meters of archived North Grip 2 ice for this project. All right, Joe Morgan cannot answer this question, although it'd be a good test to see if he was paying attention last fall. So anybody want to hazard a guess of what the 3 most important words in paleo environmental work is? Anybody? All right, I won't make you do it. Dating, dating, and dating. And this is a quote from Jeff Serringhouse. I don't know whether he lifted it from someone else. And this is important, especially if you're going to try to do you need accurate independent dating, especially if you're going to try to infer causality. So you see a change in the ice core record or some other archive, you see a change in history. If you're going to say one is somehow linked to the other, implying causality, boy, you better make sure your dating is completely independent. Because if it's not, you're just tuning to get the correlation, right? So really, really important. Dating is absolutely critical. So I'm going to say a little bit about that. So this is a 1 meter section from 380 to 381 meters depth in the ice core, in the North Grip 2 ice core. And I've plotted a bunch of different parameters, so ammonium and sea salt sodium in green, non-sea salt calcium in purplish, I guess, magenta something, and then the 2 lead measurements from the 2 ICP-MSs in the blues. And then I've plotted, just to emphasize it, I've plotted the non-sea salt sulfur to sea salt sodium ratio, and that's the one we could use for dating. So would anybody like to hazard a guess as to how many years you see across this? Remember, there's an annual cycle in all those chemicals. So, right? So 1 meter, and we've got clearly 1 annual cycle, 2 annual cycle, 3, 4, 5, right? So if we date this, again, we're just going to start at the top, and we're just going to count backwards. These annual cycles, we're going to count them backwards. So here's AD 19, AD 18, AD 17, and so forth. And you can see it's very clear. The annual cycles in this section are very clear. I mean, there's not really a lot of debate. So we dated this ice core completely, not completely, independently from 1259, the eruption of Samalis in Indonesia, a very distinctive marker in ice cores. We measured, we started there, and we just counted backwards 1 year at a time for the whole record, all the way back to about 1200 BC. So 20, whatever that is, 3,300 years, something like that. Or maybe 35. Anyway, so that's how we date it, and we're gonna, in this case, we use the midwinter non-sea salt sulfur to sea salt sodium minimum that we can see in the ice, right? So we just arbitrarily assign this date of January 1st every year, and that's how we date the core. We'd also like to be able to evaluate those chronologies in some way. So the dating of the ice core referred to as a chronology. We'd like to be able to date it in some independent way. And the way we do that is we compare it to beryllium-10, and we can do it, it turns out, with linked the tree ring records to the ice core records through cosmogenic nuclides. And that'd be 10 beryllium in ice and C14 in wood. We can do this at annual scales using these very high frequency 1 to 2 year events that were reported by Miyake originally in Nature. And Michael Siegel, that Joe mentioned, that Michael Siegel was, really took this and ran with it. Or we can do it at decadal time scales, published by Adolfi and Muschler, their techniques. And the advantage is that we can then look at the ice core chronology that we developed, and we can try to do something, we can evaluate it and try it independently and try to assess the uncertainties in the ice core dating. And I'm not going to go into too much detail, but we did this. So this is our age scale minus the NCAL tree ring age scale. And what you see, the gray is their 1 sigma uncertainty in their dating. And you can see that our dating fits within their 1 sigma. So from that, we infer that we've got about a plus or minus 2 year maximum dating uncertainty in our record. So to say to a historian, I think it's safe to say to a historian, or certainly to an archaeologist, that you have 1 to 2 year uncertainty in your dating 2,000 years ago is a pretty nice thing. We also did that with the Rossmann et al. Or the Hong et al. Dating those 18 points. We evaluated their age scale. And age scales have evolved a lot in the last 30 years, as you can imagine. And it turned out that they were about 31 years off. So historians were using that information to infer things, and not only were there hardly any samples, but they were also misdated by about 30 years in antiquity. So things have improved. Another question is lead provenance. So archaeological evidence suggests that Western Europe and China were the sort of the 2 possibilities for where these emissions could be coming from. So the question is, how do we know this is European lead and not Chinese lead, right? And the way we know that, well, first of all, we built on Rossmann's results. So Kevin Rossmann had measured the isotopes in those 13 samples, as I showed you at the beginning. And then if you plotted on 208 over 207 and 206 over 207, and you plotted in this space, you can see that they kind of fall along this line right here. And these circles represent different sources, different ore bodies in Europe. And it looks like, you know, all these measurements are consistent with a mixing model of European lead. So we can't say it is lead. It is from Europe. What we can say is it's consistent with Europe, right? So it could be coming from China, still, based on just the isotopic evidence alone. So we took that idea and we kind of, well, first of all, let me say, so possible emission sites are in Western Europe and China during antiquity. Central Greenland up here is a long way from those lead silver mines in antiquity down in Europe. So we're looking at basically transport from down here all the way up to Greenland. So long-range transport is implicit. Of course, it's even longer from China, right? So we can use very much a state-of-the-art atmospheric model to investigate this. This is this FlexPart model that Andreas Stoll and Sabina Eckhart contributed. to do this kind of modeling, basically you have a source receptor. So if you're doing it in the forward direction, you start with the source, say the lead emissions, and you have the receptors out there, and you transport the lead from the source to the receptors. You can run it in backward mode as well and look at the receptor to source relationship. We need to have very, very detailed atmospheric fields to do this kind of work, and of course, they don't exist for antiquity. So we used the 20th century reanalysis fields and assumed that the meteorology was basically the same, at least at the large scale. So this is the result. This is the ice core sitting right here in the circle. And this is where we model the emissions coming from down in here. And this is using this in backward mode. So this is this receptor to source. And what we found was that NGRIP2, the ice core site, was about 10 times more sensitive to European emissions than it is to Chinese emissions. So it is possible that you're getting Chinese emissions, but they would have to be extremely large to overwhelm the Greenland signal. Right? So you can see China over here, they're very small numbers, and we're bigger numbers in here. So from that, we think between the isotopes, there's one more slide on that. We also looked at the fallout pattern as you moved away from the emissions areas, the hypothesized emissions down here, and we looked at peat bog records, published peat bog records as you moved away from this, and we would expect that to drop off more or less exponentially as you move away from the source, and that is indeed what we found. You can see the black are the different peat bog records, and the red is our record. So it looks like it behaves as though the source is in southern Europe. We also wanted to do, for the first time in an ice core study, I think, we wanted to use the atmospheric modeling to assess how much variability we would see in deposition just from the atmospheric transport alone. So we used the same FlexPart modeling. And what you come up with is a year-to-year difference in atmospheric transport results in about a 60% coefficient of variation in the amount of lead that's deposited. So even if you had a constant source in southern Europe, by the time you transport and deposit in Greenland, it's going to have about a 60% year-to-year variability in the deposition. If you apply an 11-year median filter to it, the median filter will preserve step functions, but you'll knock down a lot of that variability, and we get up with about a 22% coefficient of variation. So in the paper, we always used an error bar of plus or minus 22% when we talk about the lead record. Why Greenland? Why go to Greenland to do this? You might think going to the Alps would make more sense. Alps are much closer and so forth. But unlike Greenland, alpine glaciers, unlike Greenland ice sheet, alpine glaciers are very thin, and they have complex flow histories. So if you get down to ancient history, if you get down 1,000 or 2,000 years ago, the layers are extremely thin. I mean, millimeters or sub-millimeter thick layers, making dating difficult, independent dating difficult, and I would argue impossible. It also makes it, because there's so little material, you can't do that 10 beryllium sort of cosmogenic nuclide sort of comparison. There's just not enough material, and so it makes it very difficult to quantitatively assess how good those chronologies are. And then finally, sites can be very heavily influenced in Europe, can be very heavily influenced by small nearby emissions. And this is just an example of that. So this is that same FlexPart modeling, but this time for an ice core, a theoretical ice core from Col de Dôme on Mont Blanc in the French Alps. And you can see on the scale here, we're 50 to 100 times more sensitive to emissions right around the Alps than we would be to emissions from Spain. So you can get a record, but there's a pretty good chance that record is going to be a local record of emissions from a nearby mine or a mine down the bottom of the valley below the ice core site. So there are some advantages in going far away, whereas when we're in Greenland up here, we're seeing sort of continental-wide emissions because there, of course, are no emission sources anywhere near Greenland, particularly at this time. So. Okay, so let me just walk you through the interpretation of the record. So two things. Well, first of all, we've switched from total lead to lead pollution, and we did that on the vertical axis. And we did that by subtracting the component of dust. So we measure a dust tracer, and we use the crustal abundance to subtract the potential dust component. And then we used, then we also estimated a volcanic component. Not a big deal. It's about 13% of the total measured lead is what we subtracted. So it's not a big part of the signal. We are also going to we also converted from concentration to flux. So we're looking at depositional flux onto the ice by multiplying by the water accumulation. the concentration times the water accumulation. And then we're also going to use the FlexPart modeling to convert, we could convert it, and we did in the paper, from lead pollution in Greenland to estimated lead emissions in Europe. And we can do that with the sensitivity modeling. For 1 kilogram per second of lead emission in southern Spain, the model would suggest you'd get 12.9 on average, 12.9 micrograms per meter squared of lead deposited in central Greenland. So we can use the lead pollution record to reconstruct European-wide emissions, granted with some assumptions, but so anyway, yeah, so at 0.75 micrograms per meter squared per year of pollution in Greenland would equate to 1.8 kilotons per year of emissions. And it turns out the archaeological estimates were pretty darn close to this. I think they were maybe within 50% of that number. So gives you a nice warm and fuzzy, right? Our record goes from, in this case, we're going from 1100 BC to 800 AD. So for those non-historians in the audience, that's the Iron Age through classical and late antiquity into the early Middle Ages. That includes the rise and fall of the Greek and Roman empires, right? As well as the migration, what we used to call the Dark Ages, and I think now is called the migration period. So let's just walk through it a little bit. So you can see this first rise back here. Well, what was that? And we can't say this is what it was, but it is at least coeval with the Phoenician expansion of trading from the eastern Mediterranean towards the western Mediterranean, right? And you can see that the concentration goes up initially here, it bounces up and down. Excuse me, by coincidence, this big jump happens at around the time that Alexander the Great consolidated power. We didn't talk about that in the paper because we really didn't have a very good explanation for why that would have changed lead emissions. But anyway, it rises up. You can see some big drops. And then right here, you can see this big bite out of the record in here. It rises, it drops rapidly, stays down for about 80 or 100 years. And then it jumps back up here, stays high, and then it falls dramatically right here and eventually reaches a nadir right here. So what are those? What do they correspond to in history? And if we compare them, it turns out that this corresponds to the crisis of the Roman Republic. So this is the end of the Roman Republic when everybody's fighting each other and there are civil wars. Mark Antony and Cleopatra here at the end and so forth. And that represents a very big dip in the lead pollution record, suggesting a much lower production of silver, at least in the Iberian Peninsula. So you had this big drop. And then in the 3rd century, this other dip corresponds to the 3rd century crisis of imperial Rome. Another period of political instability and military anarchy, right? So very nicely, the two big bites out of the record fit very nicely with what we know about history during this period. In between those two crises was the Pax Romana, and I'm not sure if that's an accepted phrase in the history world, but for us neophytes it is. Anyway, so this is the period, the Pax Romana is a period of the good emperors from Caesar Augustus through Marcus Aurelius, approximately 27 BC to AD 180. And you can see that during that period, emissions were quite high and fairly stable, indicating substantial growth in the Roman economy during the imperial period. You can also notice, if you look carefully at it, you can see that lead pollution rose about 10 years after the beginning of the Pax Romana, after imperial rule and Octavian becoming Caesar Augustus and taking over. It took about 10, 15 years for that to rise, maybe closer to 10, I guess. And then it also drops, the lead pollution dropped quite dramatically, about 15 years before the death of Marcus Aurelius and the end of the Pax Romana. So the question is why? When Andrew and I first saw this, we were a little bit puzzled by it. Well, it turns out that when Octavian took over as Caesar Augustus, he didn't immediately seize control. It took him about 9 or 10 years to establish control over the provinces in Spain and Gaul. And pretty much exactly when it should, the lead goes shooting up. And the reason that is, we think, is because of large-scale administrative changes that followed this pacification. So it was all about organization, all about getting those slaves into those mines and having them mine like crazy and smelt like crazy, right? And it does coincide with this very immediate and persistent increase in lead. And then on the other side, this drop on this side corresponds exactly, to the year, always keeping in the back of your head plus or minus 1 to 2 years uncertainty of the age scale. The advent of the Antonine Plague, there were 2 great plagues in Roman antiquity. One was the Antonine Plague, the other was the Plague of Cyprian. And you can see we get this big drop in 165, and the drop continues to 193 more or less. And that's thought to be the smallpox, killing off roughly 1/3 of the population of the Roman Empire. And then the nadir of our record occurs here, and that exactly corresponds to the plague of Cyprian, which I think historians aren't quite sure exactly what caused that. But again, a big die-off, the other great plague of Roman antiquity. Right, so very nice agreement with the historical record there. And then finally, linking back to the economy, we've plotted silver and Roman coinage. So this is the amount of silver per Roman denarius coin. And you can see that the red, so this is based on hordes, measurements in hordes, and you can see that the coins, the fineness in the coins, the silver content in the coins drops off really pretty much in parallel with our drop-off in lead pollution, and what we would postulate is effectively a tracer or an indicator of silver production in the Roman Empire, at least from Spain especially. And then it got so bad that after the plague of Cyprian, the Romans abandoned silver coinage at this point and went to a bronze and gold coin setup. Again, you can see the agreement is very nice with our record. So let me conclude by saying, I hope I've convinced you that ice cores collected from glaciers and ice sheets can contribute to historical studies. Glaciers, one of the big advantages of glaciers is they sort of consistently and objectively record pollution and history, environmental history. There's nobody making a decision about, well, we wrote this or we found the papyrus in the mask of an animal or whatever. There's nothing like that. It's a pretty objective recorder just sitting out there recording information year after year, century after century. It does have its variability, as I mentioned, that 60% coefficient of variation, but at least it's something we can quantify and work with and evaluate. Continuous measurements, I hope I showed you that are much more efficient and especially much more cost effective than discrete measurements. Distal records do have some advantages over proximal, particularly if proximal to potential sources. Understanding the atmospheric transport and deposition is really, really important, we feel, and I think is the future. And then dating, of course, as usual. And then replication between sites. And we haven't replicated the Roman period yet, but we have replicated a lot of other periods in the lead records, and we get very nice replication. For the lead record, I hope I've convinced you that lead closely tracked historical events during antiquity, that periods of social unrest coincided mostly with downturns in pollution. Unrest definitely, but wars sometimes increased, sometimes decreased. Plagues were especially had a major impact. The Pax Romana, contrary to the previous interpretations on those 18 points, the Pax Romana is seen now as a period of strong economic growth. And then finally, the silver in the denarii declined in parallel. In terms of future plans, obviously we would like to extend these records and this analysis in either direction. We'd like to go back from the beginning of the Iron Age back into the Bronze Age and the collapse of the Bronze Age and all that sort of thing. And we'd, of course, like to go this way. We're working on this because we have these records, but as I'll tell you in a minute, we don't have these records, although we're working on getting them. We'd also like to take the work that Joe Manning has done, and this is what we were talking about yesterday and while we were eating many times. We were talking about extending this linkage between explosive volcanism, climate, and ancient history or historical events. Back in Joe, in this paper, he worked on Ptolemaic Egypt. We'd like to, of course, go back in time to the Bronze Age collapse and the New Kingdom and so forth. Well, you might say, well, Joe, just go do it. Joe's, just go do it. But fundamental to both of these objectives is collection and development of much longer, accurately dated records of these ice core records, right? The problem in Greenland ice cores is that you end up hitting the brittle ice, the overpressured brittle ice at about 600 meters, which corresponds to about 1000 BC roughly, depending on the site. And when you hit that brittle ice, as soon as it's overpressured, you bring it up to the surface, you drill it, you bring it up to the surface, and if you're not extremely careful, and sometimes even if you are extremely careful, it explodes. And that's because it's overpressured, so it explodes. But you can imagine for our continuous analysis, that makes it very difficult to measure or impossible to measure it. So then you say, well, what about all those coastal domes or small Arctic islands in the Arctic Ocean? Well, the problem there is those are like the alpine cores. They tend to be relatively thin, and they thin too rapidly to get any kind of independent dating. So we analyzed one from Neuse Peninsula last year or 2 years ago, and the annual layer thickness at 1 AD, let's say, is on the order of 1 millimeter thick. So very difficult to date independently. We can get a record, but we can't date it independently. And if you're going to do this historical work, that's what you need. So anyway, thanks, and happy to take any questions. And just for you historians, there's the famous Andrew Wilson from Oxford helping us. He came out to the lab and helped us analyze the core. So anyway, thank you.
Thanks a lot, Joe. That was a master class in ice core analysis. Questions? Comments?
Come on, you historians.
Thank you very much. That was much above my pay grade. But I had a question about what can and can't be measured. Would it be possible to measure tin, given its significance in the creation of bronze, and it's perhaps being able to help with problems of identifying where the tin was coming from during the Bronze Age?
Yeah, it's a good question. So when the Oxford people first came to me, they were really hoping we could get copper because of the bronze connection. And it's a signal-to-noise ratio issue. So there's quite a bit of copper out there in dust and seawater and so forth. And so the background variability is reasonably high. And the pollution signal is relatively low. Unlike lead, they're not losing that much copper. We'd like to measure silver as well, but again, silver has the same problem. The signal-to-noise ratio just isn't there. Now that said, Hong reported measurements of copper from those 18 samples. He reported measurements of copper, but we measure copper, but we just don't see any signal yet. Now we could put more effort into it. Maybe that's what we'll do if we're successful in getting funded to collect more cores. So. And tin, by the way, tin is in the same boat. Tin, zinc, things like that have quite a high background variability, so detecting the pollution signal is hard. So.
Thank you.
I can speak loud enough.
Okay.
If you want to get an associated element with the material that's being smelted, you should look at arsenic.
So arsenic, again, is a difficult one. We would have to, it turns out that arsenic has isobaric interferences in the ICP-MS. So we would have to dedicate one instrument just to arsenic if we were going to measure arsenic. We have measured antimony as kind of an indicator, a proxy, if you will, of arsenic. And we see a lot of recent antimony pollution. Very clearly with the coal burning era, you can see big increases in antimony. But we don't see it in this period. So.
Ores that they're smelling are arsenic-rich ores.
Again, I think it's a signal-to-noise issue, and yeah, maybe we'll redouble our efforts to try to get it.
Can you simultaneously look for some climate signals? I mean, there were some fairly rapidly changing climate signals through this 1,000-year period that you described here. Can you look at that as well somehow?
Sure, and I guess one of the questions is, so the focus of this study was specifically on the lead pollution as an indicator of the economy. You could imagine linking volcanoes or looking at water isotopes and things like that to see if there is any evidence of climate drivers of some of that instability. So you have the crisis of the Roman Republic. Was it just societal, or was there a climate driver behind it? Certainly with all the things we measure with dust for aridity, black carbon for biomass burning, water isotopes and so forth, we measure a lot of things that you could use and do use as climate proxies. But we haven't done that yet. So actually it's one of the things we were kind of talking about.
Everyone's being very shy.
Thank you. That was really fascinating. And I'll confess up front, I haven't done science in a very long time, so please forgive me if this is a silly question. But I'm really interested in the comments you made about the distant sources of ice and the more localized sources of ice. And I'm wondering if there's any way that the more localized sources could perhaps refine the picture or contribute to the picture that you've given us here in any meaningful way.
Yeah, no, the question basically revolves around, are you interested in those local sources or not? because the peat bog people, for instance, have been looking and using peat bogs to study local sources of pollution for decades. And so that's the question is, if you can see through those local sources, or if you're interested in those local sources, great. But if you're not, there's always this danger you're going to be swamped by those local sources. And then there's the dating. The dating question is huge, right? I think a lot of the alpine cores are basically thin. Many of them are thin to the point where you can't see, I mean, you can't even guess what the age is prior to about 300, 400 years ago. And others do have a more uniform layering, but again, you have no way. There's the other thing I didn't mention is they tend to be dirty. You know, an alpine core, you can throw a rock and hit something at the surface, whereas in Greenland, you know, we're 500 kilometers from the nearest rock at the surface, and so consequently, they're much dirtier. So seeing volcanoes, detecting volcanoes for validation of your age scale and things like that, much more difficult than in the alpine and then in the polar ice cores. So.
Your data set ends I think just before the Vikings got to Greenland, which is, that might be a local source. Is that right, or did I read your diagram? You're
talking about that increase in about 800, this one. Yeah. You're talking about this increase here?
Yeah.
Yeah, so the historians, we were milking the publications, so we stopped at 800 because this is really about classical antiquity. We do have records that go, in fact, a number of records that go up to the present, and that's the thing we're working on now is trying to interpret the Middle Ages, the lead records in the Middle Ages. I think most of my historian colleagues thinks this is Charlemagne and the Merovingian, something like that, kings. So just to show you, you said you hadn't done science in a while. For me, I hadn't done history in a long time. So when I first met these guys from Oxford, and they shook my hand and said they were classicists, and I tried to act like I knew what they were talking about. And as soon as I got on some time myself, I looked up on the internet, what the heck is a classicist? So now I know. So, but anyway, so yeah, Charlemagne, and then the other thing is, so there I think we're going to have to look at patterns. Of course, we want to get isotopes to try to pin it down, but we're going to have to look at patterns, including the peat bogs. And I don't know if you noticed earlier, but that event was in some peat bogs and not in others. And I think what that's telling us is that I don't think that's Charlemagne after all. I think that's Mendips in Britain. I think that's lead mining in Britain. But we shall see, so stay tuned.
How useful are these measurements for understanding things in the southern hemisphere?
Yes, that's a great question. So, of course, transporting aerosol in the troposphere across the equator is virtually impossible because it either gets rained out or it doesn't circulate in the right way. You can get some stratospheric transport, but probably not of these things. We do work in the southern hemisphere. We published a paper 3 or 4 years ago looking at lead pollution over the last 400 years based on an array of ice cores. And Brian Skinner's colleagues are responsible for this. In 1888, pollution in Antarctica turned on, almost like a light switch. It went from low levels to all of a sudden high. And that was, it correlates, and the isotopes correlate exactly to the beginning of mining and smelting in Port Pirie in South Australia. And literally in 1 year, you can see it all over Antarctica in 1 year. And it's amazing. So the other thing that's amazing is that lead pollution arrived at South Pole 22 years before Amundsen and Scott. So it's hard to imagine they were skiing over, clearly polluted snow on their way there. So I guess Scott was trudging and Amundsen was gliding along on his skis. But anybody else?
Throughout the period, do you see a change in the potential locations for where the lead's coming from, that certain areas seem to shut down or stick?
So we need to rely, this record being so distal, again, we're focused on the big picture, almost not continental scale, but certainly largely regional emissions. One of the reasons for that whole coefficient of variation analysis with the modeling, the atmospheric modeling, was because I had to stop Andrew from seeing a bump and saying, oh, that's the destruction of the Roman 2 legions in the Teutonic forest or something. And I was trying to pull him back from over-interpreting the record. So we certainly see spikes, whether they're just transport spikes or maybe volcanic spikes, we don't know, but the overall pattern is consistent with the pollution source. Yeah, so for instance, this peak right here, everybody wants to know what that is. And my guess is it's a volcano. And my guess is it's volcanic tephra. So.
I'm just curious, are there any anthropologists who are also interested in geochemistry? I mean in terms of lead poisoning. Are there remains in any of these mine sites that are looking at the bone composition?
Yeah, that's a great question.
The tissues?
Yeah, so certainly people are looking at teeth and at bones for lead in those two archives, let's call them. And in fact, we're working on that. I was telling Joe and others at lunch that we're working on that. No, it was earlier than that. We're working on using our lead record to try to assess background pollution exposure. So up until this time, if you read books about, some people, there was actually speculation that the fall of the Roman Empire was because of the health impacts, especially on IQ and things like that, of the elite. I don't think that's, would you say that's, I think that's, most people wouldn't believe that was significant in the fall of Rome, but I don't know. I'm not a historian. But anyway, we're interested in the atmospheric background level. So we can now, with this modeling and these emissions, we can assess with modeling what the concentrations were likely to be and assess sort of what the background exposure to lead was in the general population. So epidemiological study of it. So, but there are measurements of bones of lead that are published in the literature. Our challenge, I think, is going to be finding people who are separate from, say, leaded pipes or drinking lead-sweetened wine and things like that. It's going to be finding that background. So this is the background concentration, not in addition to any exposure you'd get through food or water or whatever. So, yeah, it's really sad that in the mines, I don't know if those of you who know, the things I've read suggest that the life expectancy of a slave once he entered the mines, in the lead mines, was 6 years. It would have been a grisly job and a grisly death, I think. So anyway.
And you mentioned that isotopic analysis is helping for provenance. Is there a way to improve we make it more sensitive? Not just comparison of China and Europe, but even within Europe or in different regions. Is there room for improvements in that?
Well, so the question is about lead using more detailed measurements of lead isotopes to make a more detailed study of lead provenance. Both during this time period and during, well, both directions, right? We'd certainly like to do it that way and that way. And one of the reasons that we stopped the analysis here in antiquity is because once you get over here, now there are lots and lots of sources. And so we really do need to have isotopes to help us tease that apart. The problem, so I've contacted the manufacturers of our ICP-MSs and the people who have, maybe you have a multi-collector ICP-MS in this building, I don't know, so maybe I should talk to somebody. But anyway, I've contacted their research groups in hopes of getting them to try to make measurements at these levels, very, very difficult measurements to make. And basically all the manufacturers I've talked to have said, we can't do it. So we have to go someplace else. Anyway. Yeah, we'd very much like to. We have samples through this whole period. You remember those fraction collectors that were built into the analytical system? So we have samples going all the way through there that it's the same water that gets injected to the ICP-MS. So we know we can monitor all the contamination issues. So we have samples going all the way through this, and we'd like to run those samples for lead isotopes. But as I said, they say they can't measure it. So even the latest and greatest can't measure it. So I guess the only option is going to be we're going to have to evaporate them to concentrate the lead, and that's the only way. But that's a lot more work than just handing somebody a bottle and running it through their multi-collector ICP-MS. So that's a good question, though. Jen.
Can you talk a little bit more about the transport models and what we know? I mean, obviously we have really good data about the modern transport issues, but I'm thinking back in time and bigger changes in the climate system. Are there simulations to try to perturb those or imagine how it would affect? Or we sort of just assumed that it was relatively stable.
In our case, we just assumed it was stable. And it's because you need such sophisticated fields. And so when we talk to, what's her name, Betty Otto Bleisner, I think it is, at NCAR, you know, the uncertainties that would be associated with trying to have atmospheric fields for this time period are much greater than, just wouldn't work. So we're really kind of stuck. I mean, the issue for this situation was, an alternative explanation to this would be, was there a major circulation change, like a change in AMOC or something like that, right here, right here, right here. And nothing else that we measure in the ice cores, those 35 different things we measure, none of them show anything that suggests a climate change at that point. And to my knowledge, there's no other evidence from trees or anything else of any significant change in circulation. But it is always an issue, of course. It's always out there that maybe long-range transport shifted enough to actually create an anomaly. But yeah.
You talked about volcanoes eruption as a source of dust and anything. Do you have correlated plot with the historical eruption in record?
Definitely, yeah. So you'd be amazed, though, at how few eruptions actually have an independent historical date on them. What's the oldest? Do you know what the oldest? Well, Santorini, I guess.
44 for sure.
But we don't know which eruption it was. We don't know what erupted, right, in 44 BC.
Yeah.
We know there was a major eruption. There were two in 40, we think maybe 44, 46 BC, but we don't know what their source was. But yeah, definitely whenever there is a date that we can compare to a radiocarbon date or a historical date, we tie that to the volcanic record. And of course, we look for tephra and tephra is a little bit like the provenance question. You can only say that it's consistent with this source, but you can't really say it is that source because you could have multiple volcanoes with reasonably close to the same source. So.
Any other last minute? If not, please join me in thanking Jim.
Thanks for coming.